It's me again. I'm here to introduce our next speaker, who is Dr. Catherine Lai. Catherine Lai is a lecturer based in the Centre for Speech Technology Research at the University of Edinburgh. She specialises in automatic spoken language understanding, affective computing, and multimodal speech processing. Take it away, Catherine.
Hi, everybody. So I'll just, thank you for the introduction. I'll just share my slides. Okay, so I hope you can see the slides. So yeah, please shout out if anything goes awry or anything like that. I can only just see the participant list. So yeah, so I'm from the Centre for Speech Technology Research at the University of Edinburgh, and I've been working in linguistics and computer science for quite a while now, going backward and forward, and I'm really interested in how we can basically use computational methods to understand speech from a data-driven perspective. And what I've learned in my time in this area is basically we need to not just do the machine learning part, but also take some of the knowledge from domain experts like linguists, and to try and understand what we're doing actually and how we can progress further. So I'll talk to you a little bit today about my some of the work I've been doing recently. So when we think of speech technology, we basically think of two main subfields, I guess you'd say. So you've probably heard about this a lot in the last couple of years as being something that's kind of really ready to go. And you either hear that these problems are completely solved or they're not solved at all. So you might have come across automatic speech recognition, or ASR, which is generally getting speech and converting it to text, or the opposite, so speech synthesis, which we usually refer to as text-to-speech, so going from words and generating speech from that. But what I'd like to argue is that's really just the starting point of speech technology, and there's a lot more to speech than just this, and that's what we have to kind of get to if we want our speech technologies to work in real world contexts. So if we just consider something like how we go from audio to text, the general basic underlying premise is that model that we have is that we take a speech waveform, which you'll see at the top represented in as the waveform with a pink background. We do some feature extraction, which generally has relied on some sort of signal processing to get some features. So you'll see the spectrogram there in gray as a representation of the speech in terms of its frequencies. Then we use something like graphical probabilistic models like hidden Markov models, or nowadays neural networks, to model the acoustic sequence. So how do these 10 millisecond sequences of 10 millisecond feature vectors, how do they relate to specific sounds in a language, and then to words? And then from a language model perspective, how do we go, what's a likely sequence of words in a model? And so if you've ever tried some ASR in the last few years, or you've looked at some automatic captioning on lectures, you might have noticed that sometimes the language model is very strong and it will overwrite what was actually said by something that was kind of deemed to be more likely based on the training data. And that's an issue that we have to deal with another day. But then we get words as output, and generally we see that, you know, ASR today is pretty decent. So this is a bit of a snippet from a speech by Nicola Sturgeon, and it got pretty much all of the words right. The problem was that the words it got wrong were the most important ones. So here you can see kind of down at the bottom, it transcribes terms of break at Norman. So that should have been terms of Brexit are known. So it's getting the most important words wrong in that case. So that's just to try and emphasize to you that the training data is actually really important in these technologies. So this ASR system was trained on data that was kind of collected before Brexit really became a huge talking point. So it didn't have it in its vocabulary, and so it can't transcribe it correctly. So that's one of the main goals of current ASR, is to just basically try and adapt to different situations and move with the times as our vocabulary changes and the way we interact changes. But even if we have perfect ASR, there's still quite a long way to go. So if we just consider text versus speech, you can kind of see that there's a lot of stuff that's kind of missing if we just get the text. So if we just look at this bit of text here, which is from a conversational speech corpus, and it's been automatically, well, okay, in this case it's been manually transcribed, but the way that you would get for ASR, so no punctuation, no capitalization, no chunking or anything like that. It takes a little bit of a while to try and figure out what's being said. And if I tell you that there's a quote in there, it's not actually clear where that starts and ends. So there are several different ways, several different points which you could say are a quotation just based on the text. So here's just 3 in purple. But if you actually listen to the audio, which hopefully will work.
So I said to him when he left, if you remember, I told you, I said to him, don't forget, Dave, if you ever get in trouble, give us a call, you never know your luck.
So hopefully you could hear from that when you actually have the speech signal, you can actually determine that it's more likely to be the last one. So the speaker kind of changes his voice during the quotation. And in terms of, so that was a bit more of like how the aspects of speech give you something about structure, but it also gives you something about speaker affect. So it tells you how somebody feels about what they're saying, or another dimension of what they're trying to express. So in this clip, this is Unbreakable Kimmy Schmidt. So she's going to say the same thing twice in 2 different styles.
I'm so sorry. We really care that he's your friend. Could you guys be any cooler?
Oh no, Kimmy. The internet doesn't talk like that. The internet talks like Chandler.
What? No. I'm so sorry. We really care that he's your friend. Could you guys be any cooler? You can't tell when someone's being sarcastic on the internet.
Okay, so the takeaway is you can't tell when someone's being sarcastic on the internet, but to understand that the second reading is sarcastic, you have to understand the social context in which Kimmy is talking. So that is, how did people talk in the 90s, specifically in the TV show Friends? But hopefully that gets across to you what the sort of things that are missing when we just have text. And so that's why I'm really interested in this question of how we say what we say and what does it mean. So that usually falls under the rubric of speech prosody, which is not a commonly known term, but you might have thought about it more in terms of intonation. So the pitch, the energy and the timing of your speech. So are you talking really high or low? Are you loud or are you quiet? Are you talking really fast or maybe a bit slower? And also things like your voice quality. So are you kind of tense? Does your voice sound kind of harsh, as it might do if you're a bit nervous, or does it sound a bit breathy? So oh, sorry, I just wanted to make sure that people could hear. So yeah, so harsh voice and breathy voice, they're kind of physiological things, but they also have their own social signals. But basically, we had to add all this different stuff to our text messages. So these emojis, they're really pervasive now, because you don't just get those things from the transcript. Whereas when we're talking to each other, we don't generally have to, actually make these faces. It's through the speech. So another point is to think about, how we communicate in text and how we get these sorts of prosodic effects, just using other modalities as well. But I'm going to talk to you a bit more about speech. So just another example of how you can vary your prosody on a single response, and it can tell you different things. This is just the word really, spoken in different contexts.
Really? 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 Really?
So you can hopefully tell from there that the speaker had kind of different level of engagement to the person they were talking to. So they might have been a bit more surprised in some cases, or a little bit more kind of not caring that much, let's say, in other cases. And this can determine for your automated dialogue system what should happen next. Should you talk more about what you were just saying? Should you explain more, give more evidence, or can you just kind of move on? So these sorts of ways that we interact with speech are really important for developing automated systems and interactive systems, but they're not really dealt with if we just go go to text and try to make decisions from there. So how do we interpret prosody? Well, we have to consider a lot of things. So the linguistic structure, how we put things together, how we put individual sounds together, how we put utterances together. So that's the discourse structure. What are the higher level discourse features? So are you trying to complete a specific task? So it's quite different the way that you would talk if you were trying to defuse a bomb versus if you're just chatting with your friend over coffee. What sort of role do you have in the dialogue? Are you speaking in a specific style? And also situational and speaker characteristics like your dialect. So the way people use intonation in Belfast English is very different to in standard Southern British English, and different again in Australia. You might vary depending on your emotion or your stance towards a person that you're talking to or a topic that you're talking about. So there's a lot of information basically riding all on this wave, and what I'm interested in is how we can use computational methods to understand what's going on, and so that we can get a good coverage and build sort of robust models about how we understand what we're talking about, but also to understand human communication on a broader level. So just to say really quickly, it does help. It does help to incorporate all these different features to traditional and natural language processing tasks like summarization, quotation detection, I mentioned before, discourse, relation detection, paragraph segmentation, I'll talk a little bit more later. And it also helps to incorporate this into affective computing, so things like emotion recognition, sentiment analysis, predicting how people felt about a specific meeting, and stance recognition. But all of these works tend to be on very limited domains, and so one of the big challenges that we have now is how do we make things that are generalizable and robust across different domains, and not just so dependent on the specific style of the training data, or perhaps just understanding where these models will work and where they don't work. So basically we've learned from this that structuring machine learning models to reflect our prior knowledge of prosody and discourse and dialogue structure really helps, but we've only just scratched the surface. So we're only really starting to get to the point where speech technology is good enough to get to these sorts of nuanced effects. And so it's an exciting time, but it's also a very open-ended time, and we're kind of having to carve out like where we're going. So I'm just going to talk to you about a few different studies that I've done, which are going in different directions. So one was to try and understand the structural properties of speech, again at a longer term level. So we just looked at how you might chunk up TED Talks just based on their transcripts and their audio into paragraphs. And so we used a large data set of these TED Talks of very diverse speakers speaking English but in different styles and dialects, and found that, you know, there were some sort of generalizable patterns across paragraphs. So they go down in pitch over a paragraph and reset, and they get a bit slower towards the beginning and the end. But what we found is that's not really enough to make predictions. So what we actually have to take into account of is lots of different features. So basically, don't worry, there's a lot of information. I'll walk you through it, don't worry. So this is some results, doing some automatic paragraph segmentation on these TED Talks. And so on the y-axis, it's a score of like how close the predicted segmentation into paragraphs was to the gold standard by humans. And on the x-axis, so across ways, it's the word error rate. So we tried using transcripts with different levels of errors. So these were different ASR systems. So up to 50% errors. So that's every second word is wrong. And what we found was we didn't do too well if we just used traditional cohesion, text cohesion-based metrics that had measured features that had worked, you know, well in previous tasks just based on text. So news story segmentation or chapter segmentation. The prosodic features did a little bit better, but still not super great, but they tended not to get worse as the error rate went up in the transcripts. We did better still if we used some sort of derived lexical features, so like information about syntax and lots of other things, but we actually did just as well if we just took the word identities, and specifically also, so this CW means keyword, so some emphasis on the first 3 words. So that's where a lot of discourse markers are found in English, so things like because, otherwise, and things like that. But we found that, as you might expect, the performance degrades as the transcripts get worse, but very pleasingly, we also found that if you combined the prosodic features and the lexical features, that seemed to ameliorate the problems with the degradation in the transcript. So that's a nice thing to know. But basically the overall story of this is that we need to combine lots of different streams of information that all kind of weakly signal different properties of the structure. And I'll just talk to you very briefly about another project that I was working on, which is more about conversational speech and detection of stance. So the goal was to develop some sort of long-term human-robot interaction experience, and this was work done with Toyota Motor Europe. And so we were kind of basically just trying to figure out what would be the basic things that we would need in order to build rapport between a human and a robot. So if you've talked to some voice assistants like Alexa or Siri lately, you'll know that they don't remember much. I mean, Amazon know everything about you, but they don't, the actual dialogue system can't really sustain long-term conversations. So people have been working on this for quite a while. So what would be the very, very basic things? So we'd want to know what people were talking about. So what people, what places, were they talking about family, work, or other things? But also, how did they feel about what they were talking about? So are you happy about your work? Are you annoyed with your family? So these are the things that we'd like to understand in order to build a long-term interaction. And so if I have a minute, I'll just play you 1 second of this call home data.
And my dad was like, why don't you call Susie? And I was like, that is the last person I want to talk to. For 15 minutes. I mean, I talked to her like 3 weeks ago. And all she did was bitch that I never paid some phone bill, which I did, and she just forgot because she spent the money on something else.
Okay, so she goes on like this. So the call home corpus is a corpus of real conversations between people who know each other really well, and they were recorded back in the olden days when long, 30-minute phone calls overseas were really expensive. So they're really happy to be talking to each other, but obviously in this example, the speakers are talking about someone they don't really like a lot. Called Susie. And so our goal was to detect these sorts of segments and also determine how the speaker felt about who they were talking about or what they were talking about. So I'll just go through this super fast, but this is basically just to say that we tried a bunch of different models. So do you just take some sort of representation of the text over the whole topic and some sort of acoustic representation of the whole topic segment, so that's multiple turns? Or do you build in some hierarchical representation? When do you fuse different features? Do you add some more information about who's the listener? That sort of thing, using some neural network models. And the main benefit of that is that they're very flexible and you can try lots of things. But the other thing is that we don't really know how to understand what they're doing yet. That's another question for another issue. And we compared this to an all bells and whistles state-of-the-art emotion recognition detection that had more stuff, basically. And basically the results turned out that, as expected, combining the different lexical and acoustic features, so more of that speech information helped for the different stances that we looked at, but there was no one model that topped everything. But longer-term acoustic features were important for some of the stances, so were you overall like higher pitched over the whole segment, versus lower pitched or something like that. But these sort of finer grained representations were useful for some other stances. So using hierarchical models helped in this case. And we did better than the state-of-the-art emotion recognition model, which was also, again, very pleasing. But possibly because those sorts of long-term contextual features weren't modeled effectively in that sort of architecture yet. So it's just something to think about, like how do you incorporate more context into your models when you're trying to do this sort of processing? That's our kind of overarching question that's kind of hanging over the field at the moment. So that's gone really if you have more questions, I'm happy to answer them, because that was a very quick whirlwind overview of some of the work that we've been doing. But if you want to take some takeaway messages from this, I would say that we've barely scratched the surface of what's possible with automatic spoken language understanding, or what's the richness of human interaction, I should say. We've barely gotten into anything of that. But to understand spoken language, we definitely need more than the transcript. So we need to go beyond just looking at text if you want to understand speech. And there's no silver bullet, so prosody helps lots of tasks, but you need the words too, and you need a lot of other things that we didn't really talk about. So how are you interacting with other people? What's the turn taking like? We need to think kind of in a longer term, so incorporating more understanding of discourse and dialogue and context, and these hierarchical modeling techniques do help, but we kind of have to draw on some knowledge of how people actually interact with each other and use language in order to develop those better. And machines can help. So from my linguistics hat, I would say that these methods do actually make it easier to explore these problems and to get a more robust understanding of how we communicate as humans. So there's a two-way street there, and it's good to be interdisciplinary. So if you're coming from another place and you want to get into data science, there is something that you can bring with you. I think that's probably beyond my realm of linguistics and computational linguistics. That's something that I would encourage you to think about. So what from your experience can you bring to a problem? So here are some collaborators, and so I'm happy to take questions. I know it's a bit late, a bit over time, but some questions, or if you want to contact me, here are some. There's my email. So thank you very much.
Wow, what a talk. I feel like we all know what prosody is now, at the very least, which is great. I really enjoyed the talk. It was great. So if we have a couple of minutes, if anyone has any burning questions, now is the time to ask. Yeah, it was so interesting. Okay, it looks like there's one in the chat. How does memory decay in the model? Does prosody decay slower than the text?
Yeah, so actually that's a very interesting question. So it seems to be that, so in a lot of like current machine learning models, the memory decays like super fast because we just can't deal with longer term memory. But I would say that prosody definitely has a shorter span than the text model. One of the very interesting things we found with the kind of conversational speech is the fact that you can kind of set a topic way back in a conversation and then kind of meander away from it and then circle back a long time later. So we really need some very long-term modeling for the text, for the actual content. For the actual prosody, yeah, it's kind of, there are some things that are very local, and there are some things that are kind of a bit more long-term, but definitely not as long-term as the text. But definitely this is something we need to, you know, try and think about much more. In a lot of applications now, we're only really thinking about maybe 3 utterances back in the conversation, which is definitely not enough for either.
Wow, great. Thank you so much, Catherine. I think everyone enjoyed your talk and your examples. It was great and it was really fun. I'm sure you're open for people to contact you if they have any specific questions, but it was a wonderful whirlwind. I really enjoyed the last half an hour. For the sake of sticking to time, I'm going to swiftly move on to our next speaker. Thank you so much, Catherine.
Thank you, Catherine. Thank you, Tolu. Yeah, so I'm going to present